Alright, this is problem 19 from page 679. If you're in my class, my expectation is that you've tried this problem before you're watching this. We're going to go through it. So we're doing proof by induction of the sum of the first n squares of odd numbers. So we've got 1 squared plus 3 squared plus 5 squared all the way through. The question gave us this formula for the nth term. Thank you for giving us that. The question also gave us this that we're trying to prove, the formula for the sum of the first n terms. If we can prove that that holds, we're done. As you've seen in the previous videos, we take each of those, we write them down over here. We need those two expressions to start, and then we take those two expressions and we plug in n plus 1. The algebra here gets a little hairy. I've already set it up for you. Take a look at that. If you need to process it, pause the video, go through that. So what this becomes, you could pause the video now and try to do the rest of this if just seeing it set up like this gives you enough. N plus 1 in the front. This is 2n plus 2 plus another 1. This is 2n plus 3. This is 2n plus 2 minus, which gives us 2n plus 1. I didn't say that. It was 2n plus 2 minus 1. Again, pause, go through that, make sure you understand what's happened there. Then we go down here. I think the green is showing up better. A sub n equals 2n plus 2 minus 1 is 2n plus 1 squared. That's my dog Theo and my son Kai. I'm going to leave it like that. Maybe we'll have to expand that out. Maybe we won't. I made the same typo as the first video. This should be plus 1s in all those spots. We were going from the expressions with n to the expressions with n plus 1. So all of my subscripts here on the left should be n plus 1. All right, our base case. S sub 1, when we just manually calculate it, 1 squared is 1. S sub 1, when we plug it into the formula, we get 1 times, when I plug in 1 right here, I get 2 minus 1. 2 minus 1 is 1. When I plug in 1 right here, I get 2 plus 1, 3. 3 divided by 3 cancels out, and so it equals 1. So, those are the same. The base case holds. The induction step. Always comes from this formula. I take all the stuff I came up with over here. So I'm taking that, and I'm putting it right here. N plus 1, 2n plus 3, 2n plus 1, all over 3, equals, going to be tight on space, S sub k, n, 2n plus 1, 2n minus 1, all over 3, plus this expression, this is what I need to show. I'm wondering, are these things going to come out to be the same? This is the first one that's kind of messy. Get common denominators. And again, I'm going to save myself some effort. I'm going to factor by grouping. I have a 2n plus 1 and a 2n plus 1. I'm going to factor that out. When I factor that out, I'm left with n times, this n goes right there, and then this 2n minus 1 plus 3 times, and then just one of these 2n plus 1s. I'm running low on space, so I'm not going to write the denominator yet. I'm just going to evaluate this. And now we have to expand this out. 2n squared minus n plus 6n plus 3. 2n squared plus 5n plus 3. I'm pretty much out of space, but you got algebra skills, so you could finish this. This down here does in fact factor to n plus 1 times 2n plus 3. You can multiply that out, see that it's the same. This whole thing is over 3. I just ran out of space, so I stopped writing it. And so I think you can finish this and show that we have in fact finished our proof by induction. And again, you see that I went from k's to n's because my brain doesn't think about that.